Next, let's talk about flow rule. So after yielding criteria has been satisfied, we then need to calculate the plastic flow based on all the information that we have. So I've mentioned in the beginning, in the introduction part, that in the flow theory of plasticity, we work in the rate form. We express the strain in terms of strain rate, and it can be decomposed into the elastic strain rate and the plastic strain rate. Correspondingly, we have the stress rate, which is the function of our elastic strain rate. So the Cauchy stress rate equals our constitutive tensor multiplied with the elastic strain rate, and then we can write it as CE times the total strain rate minus the plastic strain rate. For the plastic strain rate, in theory, they are all unknowns to us. So in theory, we have 6 unknowns because there are 6 components of the strain tensor. However, it's quite impossible to solve for a problem with 6 additional unknowns. Based on experience or experimental evidence, we have simplified the problem into 2 unknowns. One is the plastic multiplier, which signifies the magnitude of the plastic flow rate. The other one is the direction, which is represented by m, so the direction of our plastic flow. So with this composition of our plastic strain rate, we can set up our loading-unloading condition or Kuhn-Tucker condition. Similarly, as in the case of contact problems, where we have a contact or non-contact expressed also in the Kuhn-Tucker condition format, here we have this set of equations. They need to be satisfied during all stages of loading. The last one simply means that there are 3 different status during the entire loading history of an elastoplastic problem. We have the elastic loading unloading, where the plastic flow rate is simply 0, and our yield condition is not satisfied. We also have the neutral loading, which means that now our stress state satisfies the yield criteria, but our plastic flow rate is still 0. This is the case where the loading, our stress state, is traveling along the yield surface. The third condition is that the yield criteria has been satisfied and we are having a finite plastic flow. So to calculate our plastic flow, we need to dig into this last condition. Note that this equality needs to be satisfied during the entire loading process, which means that we can take the partial derivative of this quantity with respect to time and still obtain 0. So when this needs to be satisfied throughout loading history, it automatically guarantees that its partial derivative with respect to time is equal to 0. We can then decompose it, and here, if we focus on the last condition where the plastic flow is happening, we can see that f equals to 0, so the first term goes away. Lambda dot is larger than 0, so lambda dot here is larger than 0, and then in order to satisfy this equation, we must have f dot equals to 0. So this is our condition. When plastic flow is happening, we need to have both f and f dot equal to 0. This is so-called progress consistency condition. This condition is very important because we have a rate form for lambda, which is a plastic multiplier, and now we have a rate form for the yield condition, which is a function of our Cauchy stress. Because we relate the Cauchy stress and plastic strain in rate form, this additional condition will come in handy when we want to calculate our plastic flow rate. We can then write the f dot as a partial derivative of f with respect to tau, dot product with the stress rate. This partial derivative of f with respect to tau is simply the gradient of the yield surface at our current stress state where the yield condition is satisfied. This needs to be 0, and now we have a condition on the stress rate equal to 0, we can substitute the expression of stress rate into this condition, and we obtain a relationship between our plastic strain rate and the total strain rate. So here we rewrite it here, this our stress rate expression. We substitute in the expression of plastic strain rate in terms of the plastic multiplier times the direction m. So this both of them are still unknown. We substitute this expression into our consistency condition, and we obtain this equation. Here we can rearrange this equation and single out an expression of lambda dot, which is our plastic multiplier, in terms of the rest of the terms in this equation. So if you look at this equation, you'll see that n is our gradient of the yield surface at a known position, which in this case at the position where at the stress state where this yield condition is satisfied. CE is our constitutive tensor. The epsilon dot is the total strain rate. Numerically, this would be simply delta epsilon divided by delta t. And delta epsilon is a total strain increment, and this can be obtained from our displacement increment through the strain displacement matrix B. So in this expression, the only unknown is m. Now next, we are going to substitute the expression of lambda dot into the expression for the stress rate, and then obtain a relationship of stress rate in terms of total strain rate. Here I've moved the lambda dot to the very last position because it's a scalar, we can move it. And then I've substituted in the expression of lambda dot expressed here, and then we can express the second term by this expression. What I'm going to do next is to replace the dot product with matrix multiplication, and then bring this term here onto the numerator. And then we have this expression. Note that the dot products have been replaced with the matrix multiplication operation. Now we have singled out the total strain rate. Here we also have the total strain rate. So if I substitute this expression into this expression for the stress rate, we are able to isolate the tangent modulus, which relates the total stress rate with the total strain rate. Note that this tangent modulus is symmetric if n and m are collinear, and experimental evidence have shown that this is the case for metals. Basically, we got rid of one unknown, which is m, for metals. This is called the associated flow rule. So if m and n are collinear, or m equals to n, we can simply write that the plastic flow rate is plastic multiplier times n, which equals to partial f over partial tau. And f, we know the expression of f, and tau, we know when we can obtain this and evaluate at this point, which is known to us, and then obtain the expression of plastic flow rate. And we can calculate, since we know now m equals to n, we can calculate the lambda dot, and we obtain the full expression of epsilon p dot. As I mentioned, this is so-called associated flow rule of plasticity. This is basically to say that the plastic flow direction is associated with the normal direction of our yield surface, or the gradient of our yield surface. For von Mises criteria, this would be in the same direction as our stress tensor. Of course, we also have a non-associated flow rule, which means that now they are not associated. The plastic flow direction is not associated with the normal of our yield surface. And then we have to form a different function g, and this g enables us to calculate the actual flow direction m. So this j in the most generic form is not equal to f. This is the case with soil or concrete, where the friction and the influence of hydrostatic pressure cannot be neglected. However, for our purpose, which is mainly on metals, this is not an issue. We have the associated flow rule, which helps us simplify the problem. And G is called the plastic potential function. So with this, we have presented the flow rule for flow theory of plasticity without hardening. We have come up with the expression of lambda dot, which is the plastic multiplier. And for associated flow rule, we have the direction m equals to n. We have the expression of stress rate in terms of total strain rate. And these equations would enable us to solve the problem, find our stress and plastic strength at each loading increment.